We are moving to the next topic, that is hybridization. You know methane, which is tetrahedral in structure. I showed you the shape of methane, tetrahedral in structure. Around carbon, you see 4 bonds. According to that valence bond theory, orbitals overlap, or orbitals with unpaired electrons overlap. Yesterday we saw 1s orbital of hydrogen, which has got 1 electron, and 1s orbital of other hydrogen, which also got 1 electron. They overlapped, and in that new place, in that new bond formed, that new bond means 2 electrons. 2 electrons are there in that new bond formed between hydrogen and hydrogen. So similar to that, what all orbitals are overlapping in the case of carbon? We said a bond is formed by this overlapping. Hydrogen got 1 electron in 1s orbital, another hydrogen got 1 electron in its 1s orbital. These orbitals with unpaired electrons, they merged and a new bond is formed. That bond means 2 electrons. In that bond, 2 electrons are there. So in that way, around carbon, what all orbitals with unpaired electrons, 1 electron, unpaired electron are present. Let's see the electronic configuration of carbon. That is carbon 6, 1s2, 2s2, 2p, x1, 2p, y1, and 2p, z0. 2, 4, 5, 6. So here, like that hydrogen's 1s orbital that carried 1 electron, in the case of carbon, what all orbitals are carrying 1 electron? 2px, 2py. So 2px should have overlapped, 2py should have overlapped. So around carbon, only 2 bonds should be there. But we have learned in class 10th also, we learned the tetravalency of carbon. Tetravalency and catenation. You must be remembering these 2 words, very important words, tetravalency and catenation. So here, around carbon, we expect only 2 bonds similar to that one. But here 4 bonds are there. So you have to account for that 4 bonds. To account for that 4 bonds, we are bringing the concept of hybridization. We are bringing the concept of hybridization. We say valence orbitals are hybridizing, means they are intermixing. They are intermixing to form new orbitals. New orbitals. Valence orbitals 2s, 2px, 2py, 2pz. These 4 orbitals are intermixing. In hybridization, this inner orbits are not considered. We are seeing some results for that. We are manipulating a theory. This could have been happened. This could have been happened. This could have been happened. Like that, we are manipulating a theory. That is this hybridization. So to account for this tetravalency, that is 4 bonds, we are going to manipulate a theory, that is 4 orbitals are intermixing. This electronic configuration we write as carbon ground state. And scientists say carbon will be going to an excited state. How? One of this 2s electron, I am removing that 2s, sorry, 1s. One of this 2s electron, one of this 2s electron is promoted to 2pz, which is empty. 2pz, that is empty. If there is empty orbital, this promotion is possible. If there is no empty, no promotion. If there is empty, promotion of electron. So it is getting promoted. So here 1 now, here 1. So next I'm going to show carbon. This after promotion we write excited state. Carbon in the excited state. So this was ground state, carbon in the excited state. So I'm showing that 2s ka 1, then 2px ka 1, 2py ka 1, 2pz ka 1. So this is the carbon in excited state. And now they say all they intermix together. See, s orbital is having lower energy than p orbital. Their energies are slightly different. 2p orbital is having slightly higher energy than 2s. And these all intermix together. And you know that S is spherically symmetrical. S is spherically symmetrical. P is dumbbell shape. This P is dumbbell shape. PZ dumbbell shape. So these all orbitals are having different orientations, different shapes. They all intermix together. They all intermix together to form new orbitals. If 4 are intermixing, new orbitals will be again 4. Equal number of orbitals of equivalent energy. Sabka energy same, equivalent energy and identical shape. This is spherically symmetrical, dumbbell shape, dumbbell shape, dumbbell shape. Now, after intermixing, you will be getting what? 4 new orbitals. If 4 orbitals are taking part in this intermixing, 4 new orbitals will be coming. If 5 orbitals are taking part in this intermixing, 5 new orbitals are coming. That's why we say equal number of orbitals of equivalent energy. All are having same energy. Previously 2s got lower energy. Now all are having same energy, equivalent energy and identical shape. All are having same shape, and these all are on carbon. So we are going to show this on carbon. This is hybridized orbital with one bigger lobe and one smaller lobe. This is called a lobe, L-O-B-E, bigger lobe and smaller lobe. And these 4 new orbitals, see, this is the second orbital, and this is the third orbital, and this is the fourth orbital. All are residing on carbon. Since see 1s and 3p are taking part in hybridization, we call them sp3 hybridization. This is sp3. See, one s orbital and 1, 2, 3, 3p orbitals are taking part. So these orbitals are called sp3 hybridized orbital. Each hybridized orbital is called sp3 hybridized orbital. They are residing on carbon. Each one is carrying one electron. And they are overlapping with 1s orbital of hydrogen to form. See, this is 1s orbital of hydrogen. So a bond is formed. A covalent bond is formed with 2 electrons. I have shown 2 electrons here. 1, 2. 2 electrons. Similarly, here also, this is 1s orbital, 2 electrons, and here also 1s orbital, 2 electrons. Here again 1s orbital, 2 electrons. So we have explained the tetravalency of carbon. Around carbon there are 4 bonds. Around carbon there are 4 bonds. Okay. So in CH4, the hybridization is sp3. What is hybridization then? Intermixing of orbitals of slightly different energies to redistribute their energies, resulting in the formation of new orbitals of equivalent energy and identical shape. This is what is meant by hybridization. Write down, what is hybridization? What is hybridization? The process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of a new set of orbitals, SET, a new set of orbitals of equivalent energies and identical shape. What is hybridization? The process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new orbitals of equivalent energy and identical shape. That is hybridization. What we have learned is sp3 hybridization. Now we are moving to sp2 hybridization. Consider BCl3. Boron 1s2, 2s2, 2px1, 2px1. So these are the valence orbital 2p y0, 2p z0. 8th week. Okay, thank you, sir. Okay. So, gloves and all, son. Huh? I don't have gloves. Hey, office man. hai.
Ask maybe if she's not extra.
Okay. Okay. Okay, sir. Yeah. Okay, sir. So this is the ground state. So I am writing it as ground state. Boron in excited state. So here, one of the 2s electron got promoted to 2p, 2px1, 2py1, right? 2pz0. Now these orbitals are undergoing hybridization. And with the orbitals with unpaired electrons, they are undergoing hybridization. So you will be getting 3 new orbitals. 3 are undergoing hybridization. You will be getting 3 orbitals of equivalent energy and identical shape. So these 3 orbitals, each one is carrying one electron. Boron. So these are bigger lobe, smaller lobe, bigger lobe, smaller lobe, bigger lobe, smaller lobe. So these are pointing towards the corners of a triangle. Each one is carrying one electron. Right? Now, each one is called what? sp2 hybridized orbital. sp2 hybridized orbital. Now look at this Cl3. Each chlorine is having that pz orbital, 3pz orbital, p with 1 electron. So that will be making a bond with like this. One covalent bond will be formed, and here that overlapping, pp overlapping. This is sp2 p overlapping. So around boron, this Cl, this is of Cl, 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 Cl. So BCl3 is planar. BCl3 is planar with a bond angle 120. If the bond angle is 120, the molecule is planar. That is sp2 hybridization. Now sp hybridization. That is BeCl2. Example is BeCl2. Be ground state. 1s2, 2s2, 2p empty, 2px0, 2py0, 2pz0, 2px0, 2py0, 2p Z0. So valence is 2s, one electron will be promoted. So beryllium in the excited state, that is 2s1, 2px1, those are zeros. So these unpaired electron orbitals are undergoing hybridization. We call that sp hybridization. sp. So how many hybridized orbitals will be formed? Two hybridized orbitals will be formed. These two hybridized orbital sp, that this is one hybridized orbit, they will be standing far apart as possible so that there is minimum repulsion. They will be standing far apart. This is one and this is the other, so that there is minimum repulsion. So here one electron, here one electron. Now Cl, in the previous case also Cl was coming with its pz, pure orbital, not hybridized, pure orbital. So this is hybridized sp2, sp2. So here this is Cl and the other Cl. Cl. So this is Be, central atom is Be. So around Be, this is Cl bond, covalent bond. This is Cl bond, bond angle is 180, and this is linear. If the bond angle is 180, this is linear. All right. Now we are going to sp2 and sp hybridizations in carbon compounds. That is CH2 double bond CH2. See, there is a pi bond. One is sigma bond, one is pi bond. Sigma bond is more stronger than pi bond. A double bond is more stronger than a single bond. So let's see. See, each carbon is under same hybridization. What is that hybridization? You see, around carbon, one hydrogen, and one sigma bond. So three bonds are there, and this is a pi bond that is made by sidewise overlapping. Yesterday we saw. So carbon in the ground state, each carbon, this carbon and this carbon, same hybridization. Carbon in ground state, that is 1s2. Now excited state, carbon in excited state, I am showing this valence 2s1, 2px1, 2py1, 2pz1. Now what is observed? That is, only these things are getting hybridized. So here sp2, it undergoes sp2 hybridization, but this is pure pz orbital. Pure, it is not undergoing hybridization. Pure pz orbital with one electron. So here three sp2 hybridized orbitals are there. They will be standing in a planar way, and this one will be perpendicular to these three. This will be perpendicular to these three. So if I show the sp2 hybridized orbital of, these are observations are explained using theory. So carbon central carbon, its sp2 hybridized orbital is sp2 hybridized orbital, it's sp2 hybridized orbital with one electron. Another carbon is also in the same situation now, that pz orbital is towards the front. One lobe is at the front side of this board and the other lobe is at the back side of this board. But I am showing it like this, pure of equal lobes, right? Equal lobes with one electron. Similar, the second carbon is also in the same situation, and I'm showing after overlapping. With one electron, one electron. Here also there is a pure pz orbital of equal lobes. That this lobe is perpendicular and this lobe is perpendicular, that is behind the board with one electron. And this will be overlapping with 1s orbital of hydrogen, 1s orbital of hydrogen, here 1s orbital of hydrogen, here 1s orbital of hydrogen. So this will be sp2 overlapping, sp2 overlapping with a pair of electron, and these will be overlapping sidewise like this and like this. The sidewise overlapping to form a weak bond called pi bond. So carbon single bond here, this H, this H, this H, this H, and that sidewise overlapping is the second bond, that is a pi bond, which is a weaker bond. Next we'll be learning sp hybridization in carbon compounds, that is in hydrocarbon, that is sp hybridization in ethine. This is ethene. This one ethene. Previously we learned methane. In ethane, in alkanes, sp3 hybridization in alkenes, sp2 you can see, in alkynes, sp hybridization. Thank you.